that down there. Let's see what we got. All right. So last time we were starting to introduce Java and objects in the context of Java. We talked about the kind of, it's called like upgrading from structs. That's probably not the right word, upgrading, but looking at additional options beyond structs that maybe do something extra for us if we were to need that. I mentioned that structs do not exist in Java. And I'm going to talk about that a little bit more here in a second when we go back and look at our fraction class. I think we started writing in Java. I think I mentioned it last class, but it is an important thing to think about when you move between different programming languages. We talked about the class keyword. So all object-oriented languages, or maybe there's some language out there that doesn't use the keyword class, but for all intents and purposes, all popular object-oriented languages, when you build an object, it's going to be inside of a structure called a class. And classes are made up of three things. So if you were to put a little asterisk at the top of a slide for an important slide, this would be one of those. Knowing what a class is a collection of 0 or more fields, 0 or more constructors, and 0 or more methods. Technically, we saw last time that if you don't write a constructor, it gives you one. Constructor that takes no parameters to make the syntax work after the new keyword. We'll talk more about that as we go through, because I will just keep re-emphasizing that idea. But this is what a class is. It holds a bunch of variables, which we call fields. It holds constructors, things we use to build instances of a class. And we're going to talk about that idea of an instance because it's related to that static keyword that we've just seen living out there right now as part of our main. We'll get into that reasonably quickly. And then we have a whole bunch of methods. These are abilities. So we're going to kind of explore that idea of constructors and methods today in the context of our fraction class that we built. So we've kind of started off with this idea of our fractions as we've kind of rewritten it in Java as if it's a struct, right? We've basically created a class that has exactly 2 fields and nothing else. And we're going to say, we're going to play the same game as structs play here. So we don't really see the advantage of this yet, but we're going to see it today. We talked about this concept of encapsulation, which we might say is the kind of the reason for using objects, where we use the example of that the object-oriented telephone from first week of class or whatever, where all the stuff, all the things that make a phone work are stuffed inside the little phone-looking container. And we know it's all in there, but it's encapsulated inside of that container so that when we go to use it, it's like we just took a phone out of our pocket and we're using it. We don't see all these details that we know are in there, but they're hidden from us while we're using it. All right. We talked about the concept of polymorphism, whether you, I mean, it's a good word to memorize just because it's fun. But polymorphism effectively says, hey, you can have more than one method with the same name, and Java will figure it out. Insert programming language in here, Java, C#, doesn't matter. They all will figure it out based on the parameters you pass. All right. If you say, oh, I want to call the version of this function that takes 2 integers, and you call it and pass it 2 integers, Java will figure out, oh, you mean the one that takes 2 integers. We looked last time at the system class. I probably still have it up. And we saw that there's a zillion versions of the println inside of PrintStream. We kind of walked the thing, and we'll see that many more times. So don't worry about it if you forgot how we got to this thing. But we see we have a whole bunch of functions called println, but they take a different type of input, either a different number of inputs or a different type of input. So when we call println passing it along, for example, it knows to call this version of it. We don't have to specify. So polymorphism is that concept of being allowed to create more than one function with the same name. So it effectively does the same thing, but given a different set of inputs. Go ahead.
Essentially, this println for Java is basically like our cout for C++.
With an endl at the end.
Yeah.
Yeah, println writes whatever you tell it to write, but then presses enter at the end, as opposed to print, which we have a whole bunch of those too. Here's your prints. We have the same collection of prints as we have of printlins. This one just doesn't have an endl on it. It doesn't kick it down the line. So effectively, the difference between those two is purely for human output. Which do you prefer? Do you, for your output screen, do you want it to kick it down the line, or sometimes does it make sense that you want to write something initially and then kind of keep adding on to that line as you have more stuff? Purely personal preference, or depends on what job you're solving. One is not better or worse than the other. All right. So that's that concept of polymorphism, that it is perfectly commonplace inside of a class to have a whole bunch of functions with the same name. Now, generally speaking, when you're writing your own classes, while you might do something like this, specifically with constructors, and we'll kind of, I'll try to show you an example of that at some point, but you might have two constructors, and constructors are always named the same thing as the class name. So you might have two constructors with the same name, and one of them takes one input, the other one takes 5 inputs. And both of them ultimately initialize the object, give it its initial values, do some, initial setup work or whatever. And in the end, you get an instance of whatever class you're calling the constructor for, but you had two different constructors you could have called. And Java will figure out which one you meant by the input you passed it. All right, we'll see plenty of examples of that. All right, so we kind of stopped here with the this keyword. So let's, we haven't talked about that at all. Let me go ahead and just give you the definition here, and then we'll kind of fill in the gaps. I think I mentioned at the end of class last time that the this keyword is not a difficult concept, as I tend to say with most programming concepts, but when you're new to it, it is a little difficult to wrap your mind around. So I'll try to pick out the highlight reel so you can really see how this keyword works. So this, I'll put it in double quotes here. One of the reasons it's difficult to teach this keyword is because it's hard to teach this without saying this. So this is how an object refers to itself from within itself. So some other programming languages use self instead of this. So that's, you'll commonly see a programming language, an object-oriented language, that instead of it having this keyword, it's called self. Okay. Now, if you just want to start your mind leaning in this direction, whether it's this keyword or the self keyword, it's equivalent to when any of us are in real life and we say me or my or I. We would think it's weird if we say, well, Mike does this, right? We say, I do this. That's mine, whatever it is. So whenever we're referring to ourselves, we already exist. And in our heads, we typically don't refer to ourselves by call it our variable name. I don't think about myself as, well, Mike wants to do this. I think as I want to do this, which would be the same thing, the programming version of saying this wants to do something. All right. So just kind of throw that in that pile for right now, and then hopefully you'll see it kind of come to fruition. Because the very first thing we're going to look at here is a common weakness, even of professional programmers, because they don't understand this concept. Right? Yet all of us understand the concept of referring to ourselves as me or I. It doesn't seem to be a real difficult concept in real life. As soon as we jump over to the code side of things, we freak out. All right, so let's look at this as an example. All right, so let's get to the code here. Did I have something written? Thought I wrote something. Oh, whatever. We'll just write a new one. All right. Again, I'm going to go ahead and change the name of this file. You don't have to. This is purely preference. Just from a teaching perspective, I'd rather not have two different things that say main. All right. So I like to call it driver. You can name it whatever you want or just leave it as main. Doesn't really matter. If I ran this guy right now, it's going to scream at me because my file name is now driver.java, yet my class name is main. It's not going to like that. Class needs to be the same, named the same as the file. So we'll just change this guy to driver. And now we'll get our hello world program. All right. So I'm going to go ahead and do what we did in class last time real quick. Might as well get used to writing some classes. I'm going to put it inside the same file for right now, even though I'm telling you this, while this will work. Typical best practices would be every single time you have a class, put it inside of its own file. So we're going to keep down this example of working with fractions. All right. So I'll be moving this to its own file shortly, but let's just get it all in one file for a second so I can kind of explain this keyword. So we're going to say class fraction. And you could put this anywhere in this file you want. Just don't put it inside of class driver. A class is kind of its own garbage bag. If you want to have more than one class, you're going to have multiple garbage bags, but not living within each other. You don't throw a garbage bag filled with stuff inside of another garbage bag and expect to be able to use both. That kind of self-polices itself if you just put everything in separate files. All right. So we're going to have a class called fraction. And what we had last time was we had this, we had a couple of fields. We had an int numerator and an int denominator. And I'll go ahead and label these guys. These guys are fields. All right. Notice that the way we write comments, same in Java as it is in C++. Go ahead.
Public class and then just like a regular class. Is that the same as like something in global or not?
No, we are going to talk about, I can't really answer that at this point without really muddying the waters. All right. It's a security thing from right now, from your perspective right now. It's an unnecessary thing.
Okay.
Because we would always add something in front of this as well, but we are purposely not putting there. So we'll stumble upon it today. Okay. So right now, if I just do nothing else, I think what we had in class last time was at this point, I've created a class called a fraction that effectively is a struct. All right. So I would go in here and I would create my fraction and I would say fraction F1 equals new fraction. I think we had an example last time. I'm going to say fraction F2 like that. And I'm just going to quickly write these out. System.out.println F1 system.out.println F2. Oh, sorry. What would we expect the output of this program to be? Remember, all programs begin and end with main. So when I ask you what the output of a program is going to be, you're going to start at line 1 of main and start asking yourselves, what do each of these guys do? What does this guy do? As opposed to what this guy does. This is kind of the lesson I'm teaching in this particular place. What is the difference between those two lines? We'll see the difference when we output here. We'll see that we get a memory address and we get nothingness. Oh, it yells at us saying this might not have been initialized. So I'll go ahead and purposely initialize it to the value that it actually holds by default. Now we'll run it. We're going to get a memory address and nothingness. So there's our memory address and there's our nothingness. We see that Java, as well as most newer languages, does police us from using a variable that we didn't explicitly put a value into. So before I said equals null here, all I did is I generated the existence of this little container that's built to hold a value of type fraction, but I have not actually put anything in there. All right. The default value that would go inside of a variable like that would be nothingness, null, just like the default value for an int is 0 typically. But I've mentioned when we first started talking about that stuff, never, ever, ever rely on default values. And we see that newer languages don't allow us to rely on default values. They will scream at us and say, look, you're trying to use something, you never actually put a value in, you check yourself. All right. So this is an error because it says, hey, you defined this variable F2, but then you tried to use it right here and there's nothing in there. Go and check what you meant to do with that. So we're just going to compare these two. I'll go ahead and explicitly put that default value in there. So when we ran this, we see that F1 gave us this memory address. If I run this guy a second time, looks like we actually, since we're using the virtual machine, it gave us the same address, but it's fine. We see that we get a memory address and we get nothingness. Why does this guy hold a memory address? What are these pieces that are out over here? We talked about the new keyword, right? What's the new keyword? Kind of referenced it as like our real estate agent. This is the guy who's in charge of going out and finding us memory, talks to the operating system on our behalf so we don't have to screw with it. It's the cleaner version of using malloc, which we did the cool kids version of that in C++, but we also saw the new keyword in C++. But, that's looks more normal. We don't want to use that. You want to look cool as a programmer. Okay. Malloc doesn't exist in Java. You have to use the new keyword. All right. So we're saying here, fraction F1, you get the value of what? Well, you get the result of a call to the new keyword. We know the result of the new keyword will always, always, always give us a memory address. Okay. And when we're dealing with objects, the new keyword is always followed by something like this. In this particular case, what is that I have highlighted? If you were to identify that at the petting zoo, what kind of animal are we dealing with there? I'll scroll up here. You have your whole class fraction up here. Is this guy right here equal to that? It's not. The name of our class is called fractions. A class always has at least one constructor, even if we didn't write it. So in this case, all we have in here is some fields, right? We have no constructors written. So since we only have fields and we wrote no constructor, Java will go ahead and pretend that we have a constructor that takes no parameters and does nothing other than supporting this syntax right here. It gives us something for the new keyword to utilize when saying, oh, you want some memory? How much memory do you need? Well, I need enough memory to hold one of these dudes. All right. So this guy right here is the constructor that it's calling. All right. Even though we didn't write one, there's this imaginary thing in here that looks like that. I'll kick it. That's what's in there right now, even though we didn't type it. Well, we typed it now. but that's what Java effectively does for you. Replace Java with C++, with C#, with Swift. They all do the same thing. If you don't explicitly write a constructor, it gives you one just to make the syntax for creating one of these guys work. All right. But now when we go to construct a fraction, okay, if we're sitting here, the constructor is like the person we've hired to build us one of these things. Okay, he's the contractor if you're hiring somebody to build your house. That's what the job of a constructor is. You give it the resources it needs, and it generates the basic starting point for one of these guys. So we know to have a fraction exist, we're going to need to store two pieces of information: the value for the numerator and the value for the denominator. All right. So I'm going to write this almost in the correct way. And then I'll tell you what most programmers who don't know about the this keyword, who don't understand the this keyword, they all know about it, but don't understand it, what they would do to circumvent this problem. So to build a fraction, we're going to need a numerator and we're going to need a denominator. And what we would do in here is we would say, Numerator is equal to numerator. Denominator is equal to denominator. We have a problem. Remember, all variables resolve to their most local definition. So in this particular case, we actually have two different definitions of numerator, two different definitions of denominator. When I say numerator gets the value of numerator, which version of numerator do I want this guy to refer to? I want him to be this guy. I want to set this fraction's numerator equal to some value. I want this guy to reference that version of numerator, the value that was passed into this constructor for this fraction to set his numerator to that value. But since they're the exact same variable name, and I've mentioned that variables resolve to their most local definition, both of these guys ultimately are that. So we are setting numerator, that numerator equal to itself. We're doing nothing. All right. So now what a programmer who isn't interested in actually learning what's happening under the hood might do is they might say, oh, well, let's just call this int n and int d. And then if we say n and d there, now it works. All variables resolve to their most local definition. The most local definition of numerator, in fact, is this guy up here. The most local definition of n is this guy right here. So you might say, oh, well, the fix to this is, oh, just make sure the variables have different names. But when we go back to kind of the rules around defining variables, we typically want a variable to be meaningful for the kind of value it's meant to hold. When I say the variable name is numerator, we could probably say, oh, that guy's probably meant for holding a numerator. When I see the variable called n, that doesn't really tell us much about what should go in there. When we look at it, we can say, oh, well, it's obvious that n is your placeholder for numerator because I didn't like the errors I was getting. Something like that. The reality is this would be poor programming practice. It'll work. But by doing this, you're effectively saying, I'm not interested in learning about the this keyword. And the this keyword is vital to be a successful object-oriented programmer. So what we would actually say here, we keep the variable names numerator, denominator there. We keep them numerator and denominator here. And what we would say is this dot numerator, this dot denominator. So when I explicitly say this dot in front of this guy, what I'm saying is don't go by the normal variable resolution rules. Don't resolve to the most local definition. I have told you where you can find this guy. This is the version of numerator that is owned by this particular fraction that we're in the middle of building. Okay, so if I'm this fraction and I'm currently being born, right? This is numerator is equal to whatever numerator is passed to me. This is denominator is equal to whatever denominator was passed to me. This is how you would specify it. Okay, so this would be correct programming practice. So now, if I run this right now, notice I'm trying to create this fraction f1, and I'm calling this constructor. We know it's a constructor because it looks like a method, has the opening and closing parentheses, but it has the same name as the class. That's a constructor. Also notice here that constructors have no return type. Whereas I'll just go ahead and write another function here. Let's have a function called display. That maybe does just outputs this fraction in some sort of pretty print way. So system.out.println this dot numerator followed by a slash followed by this dot denominator. Now let me ask you this. Did I need this dot here? Go ahead. I just wrote it like that. Is the version of denominator that's talking about right there, is that the same version as this dot denominator? All, go ahead. Somebody online?
You know it's not, but there's no level for denominator.
Well, remember, all variables resolve to their most local definition. What is the most local definition of denominator? Is there a variable called denominator in there? Nope. So as I search, as I go up one level at a time, I first look locally. I say, well, was there a denominator there? Well, first I'd probably look here. Is there a denominator somewhere in here? Nope. Is there a denominator somewhere in here? Nope. The next place in my scope I jump up to, I don't get to get into the constructor here. So my next place to look is up here. Is there a version of denominator up there? There is. So whether I say this dot or don't say this dot here, we're talking about the same thing, because the most local definition of denominator is the one owned by this fraction. Now, having said that, I would never explicitly leave the this dot off if you meant for the guy up top, even if it would work this way. I would always say this dot denominator like that. I would explicitly say which version of that variable I mean. Several reasons for this. One, under the hood, it's likely faster because you didn't make it go and search for it. You didn't search locally, then keep bouncing up. And you imagine if you have, objects inside of objects inside of objects inside of objects, you might run into having to go up 7, 8, 9, 10 levels until you find the thing you're looking for. So this would certainly be faster if you just tell it exactly where it can find it by saying this dot. The other reason for this that I obviously am very good at exemplifying here is it prevents, since most of the time we are using integrated development environments, IDEs, tools that allow programmers' lives to be easier and dense for us, does auto completion for things. When I say this dot, and then I just start typing the N for numerator, it shows me that. So then I can just press enter and it doesn't misspell it, as I'm prone to do. I have big fingers, small keys. All right. So I think it would always be correct, always be encouraged for you to say this dot whenever you are explicitly talking about the fields. Now, you would not say this dot right here, because this version of numerator is not, you don't mean to talk about that guy. You mean to talk about this dude. So if you put this dot in front of here, you are actually breaking what you meant. So you only want to say this dot if you are referring to the fields associated with that class. But my encouragement would be whenever you're referring to the fields of a class, always use this dot, even if it's not actually required, because it would resolve correctly anyways. Use it anyways. This would fall into a similar category as like when I told you when you're writing loops or if statements to always use the curly braces, even if you only have one statement following it. You'll never be wrong using the curly braces. But if you omit them and didn't know what you were doing, or just had a, it slipped your mind, you can get very different outputs in your program depending on whether it's just the next line associated with your loop or the next 20 lines. If you want the next 20 lines, they need to be inside of opening and closing curly braces. If you want just the next one line, it doesn't have to be, but if you do put them inside of curly braces, it'll still work just fine. All right, so this would be a similar encouragement to that. All right, so by writing it this way, we have now differentiated ourselves from a struct. And let me come back to that statement here in a second. I did write this up here that constructors do not have return types, where normal methods do have return types. A method is a function. It's kind of a new word to call something we've already been introduced to. Method is the object-oriented way of referring to our functions. All methods, just like all functions, must have a return type. This guy is a method. How do we know that's likely a method? We see the opening and closing parentheses. We know it's not a so at that point, we say it must be either a method or a constructor. Since classes are filled up with fields, constructors, and methods, we know this guy isn't a field because we see the opening and closing parentheses. So it must be one of the other two. How do we know this guy must be a method instead of a constructor? Because its name is display, and that is not the name of this class. So if the method name is different than the name of the class, that means it's a normal method, not something that looks like a method, but actually is a constructor, because the name of it matches the name of the class. Go ahead. Correct. Yeah. So that's why I have this in here. That's the second way you can see it, but you don't even need to rely on that piece. And the reason I emphasize that is not all languages omit the return type. So for instance, if you are coding in Objective-C, anybody know what the return type for a constructor is in Objective-C? Just coding trivia stuff. It's just something called an ID, which is effectively a void pointer. And similarly, in Objective-C, your constructor does not need to be called the same name as the class. Because by omitting the return type in Java, we now need to make sure that the programming language has a way of differentiating methods from constructors. So in Objective-C, we might call this guy a init. Something like that. Initialize. You know, you can call it whatever you want. You could call it elephant if you want. You have to remember that that's your constructor. So in more modern languages, what we do is we take out the return type and just make sure that your name of your constructor, your special kind of method, matches the name of your class. That's how we absolutely confirm to ourselves we are dealing with a constructor. It looks like a method, doesn't have a return type, and its name matches the class name. That's a constructor. If it looks like a method, it does have a return type, and its name does not match the name of the class, then it's just a plain Jane method. Still good, just a different use. Not used for initializing stuff, it's used for behaviors, doing things. All right. Now, why is it okay, outside of what I just mentioned, for a constructor to not have a return type? I did mention that in some other older languages, the return type might be something called ID. It might be something called like a void pointer. Why don't we actually have to put a return type there? Why would it be a waste of our time to put a return type there? What's the return type of a constructor? Here's us using that constructor live. Actually, we're not using that constructor live yet because now we're using that constructor live. Our updated constructor here, we now said takes 2 integers. So that no argument one has now disappeared. Java's not going to do work for us if we did it ourselves. It's not going to give us an empty constructor to make the syntax work if we chose to write it ourselves. So we need to call the constructor we built, the one that takes 2 integers. I've passed it 1 for the numerator and 2 for the denominator. Why is it that this constructor doesn't actually have to specify its return type? Not only does Java say you don't have to, why does it make sense for Java to say, yeah, we're not going to make you have a return type for your constructors? Because they could still require a return type and just say, well, if it's a constructor, just name it the same as the class. But they don't do that. They say, you got to name it the same as the class, but you're not allowed to put a return type. What is the return type of a constructor? A constructor always follows the new keyword. And what does the new keyword always do? Always gives us a memory address. 100% of the time. That's what the new keyword does. That's its job. It talks to the operating system, finds enough memory to do whatever it is you're wanting to do. We've been in here talking about the amount of memory and stuff like that. If we want to hold 100 integers and an integer is 4 bytes. We need 400 bytes of memory, that kind of stuff. But the reality is that is for us as computer scientists to understand what's happening under the hood. From a programmer's day-to-day perspective, we don't have to worry about that. We just have to say, look, Java, I want to build one of these dudes. Give me enough memory for it. I don't actually care how much memory you found for it. Just give me the right amount. Give me enough, right? And we don't have to think back. So since constructors are always called using the new keyword, they always will result in a memory address, which means that we do not have to specifically specify what it's going to return because it will be a memory address. And that's good for us because in Java, we don't have a syntax for talking about memory addresses. They exist. We see one right here. So pointers are definitely a thing. We just don't actually have a way of saying this is going to give us a memory address. So it's good news that we don't have to because we wouldn't know what to write. All right. So constructors, you don't put anything in front of them. So they almost look like normal methods. They still have parameters, just like a normal method does. Still has the opening, closing parentheses. Methods can name themselves whatever they want as long as you don't name it the same as the class. Constructors always have the same name as the class. Methods must have a return type, even if it's not going to return anything. Constructors never have a return type because they always return the same kind of thing. Make some sense? All right. And that lesson would be the same lesson in C++, would be the same lesson in C#, frankly, would be the same lesson in Objective-C and Swift, but I would have to go down a couple of caveat things. Then obviously, if we were using Swift, we wouldn't have numerator and denominator. We would pick a couple of stupid emojis for that and just assume everybody knows what that means. Don't use Swift. Unless you want to make money on the App Store, then use Swift. But do it begrudgingly. Okay. So here we have our variable f1. It's a variable named f1 that we've built to hold a fraction. And the value we put in there is a pointer to the fraction that this constructor built for us. f2 here is a variable capable of holding a fraction that we actually have not put any value in yet. If I didn't say equals null here, its current value would be null. But Java polices us and say, hey, if you're going to try to use this guy, like print it out, give it a value first. All right, so I'll go ahead and update this. Use my, let's do what, like 3/4, something like that. So now I have two different fractions, f1 and f2. If I run this, we see we get two different memory addresses, hexadecimally thing, a different hexadecimally thing, two memory addresses. Pointers clearly exist in Java. I just don't have a special syntax for working with them. Now, I'm going to try to trick you. What will the output of this program be? I got the display function there at the top, so you see what it does. Probably going to give us an error. But if we assume it didn't give us an error, what would the output logically be here? Go ahead.
It's output like the two fractions, like 1, 2.
What does display boil down to? What's the return type of the display function? Nothing. So what we would be trying to do here is we were trying to print out void. Void is not a type allowed here. Just void means nothingness as a return type. So to ask the println function to print out the value of nothingness doesn't mean anything real. All right. But this is a common mistake we make. when we start transitioning to objects, because in general, like we've been doing with C++, when we think about displaying something to the screen, we typically think about cout. But the reality is F1 knows how to display itself to the screen by calling his display function. F2 knows how to display himself to the screen by calling his display function. Internally, yeah, it does the system out thing, but F1 owns a function called display that knows everything there is to know about F1, including its fields, 1 and 2. F2 has its own version of the display function that knows all about its fields, 3 and 4. So now we'll have this guy print out our two fraction-y things. Make sense? So already now we have differentiated ourselves from structs. If we come up here to our class, it was basically a struct when it looked like that in terms of functionality. I wasn't using constructor to set the values. I would have had to then say f1.numerator equals 1, f2.denominator, or f1.denominator equals 2. Basically use it as if it was a struct. That's the direction Java took when they came out after C++, years and years and years later after C++. They basically said, oh, you don't need structs and classes like you had in C++. Because really a class that only contains fields is a struct. And I think I'd already mentioned a couple different times across several classes that that's pretty much true, but not quite identically true. And that is, we saw in C++ that structs by default are passed by value. They're passed the same way as like an int is passed or a double is passed. Whereas objects, classes, are passed by address, the same way like arrays are passed. So yeah, they basically behave the same. And as long as you're not making changes to it that either you definitely want to be felt outside or you definitely want to not have it have side effect, since Java lacks the syntax for describing pointers, a struct doesn't exist. So we actually do not have a way directly for taking a class called fraction written like this, which we've written to function like a struct. We don't have a way of directly saying, function, here's my class, my struct class. Make changes to it, but don't make those permanent. Because in Java, classes are always passed by address. We don't get to specify. In C++, structs are passed by value, objects are passed by address. In Java, we do not have structs. We only have objects. And if we make an object function like a struct, we can only do that up to the point of how it's passed. Once we get to how it's passed, it is passed by address every time. Now, there is a little bit of a hack. I think I probably mentioned it one other time. In Java, we have this concept, well, in all object-oriented languages, we have this concept called inheritance, which we're not going to talk about yet, but I'll at least exemplify it here. So objects are built in terms of a parent object. So a print stream, that's what println comes from, is actually a superset of filter output stream, whatever that is. So a print stream has everything that a filter output stream has, and then it further differentiates itself in whatever is written here. A filter output stream is actually an output stream. So it gets everything that output streams have, and then it differentiates itself a little bit more. Every single object inside of the Java programming language comes from object, the top level object. All right. So I guess we got an announcement, and then I'll keep going with this.
Just real quick, we got a CS Club on Wednesday. We're going to be playing retro games, PlayStation and N64. So open house.
Hold up, when?
What, it's Wednesday?
Yeah, Wednesday, 3 o'clock, end time is.
Okay.
Discussion.
It starts Wednesday at 3 p.m. So a week from yesterday, right? Wednesday at 3 p.m. over in computer science lobby.
Yep.
Okay. And we're going to be doing retro video gamey stuff. And I guess
Count me in,
say this again.
count me in.
Oh, it ends at whenever it ends.
Yeah.
We don't have a specific. I'm guessing it'll probably go for at least 2 hours, 3 to 5. It's probably definitely safe.
Yeah,
Yeah.
it's gonna be open for a while, that's the point.
Yeah.
But, I have an announcement on the CS Club Slack where you can register for our head count. We're trying to figure out how many people we're gonna have so we know how much food to order.
So if you go on Slack, so this is for the online people,
Yeah.
because we have a lot more online today than
Okay.
here, obviously. For the online people on Slack, there's a CS Club channel and there's a sign up sheet for this. So they make sure you're getting snacks and stuff or whatever. What are
We're
we
ordering Jimmy John's. so-
getting? Jimmy John. So if you want food, make sure you sign up so they get enough food.
Got the QR code here too for building new orders.
All right.
Thanks a lot, man.
All right. Are you gonna sign me up so I don't forget? I know you sent me I know you sent me a I have it on my calendar. So, but in case okay, thank you. I'll be there.
I said count me in, but okay.
Say this again. I'm sorry.
I said count me in. but
Okay. Well, go on to Slack and sign up do the sheet so they make sure they get enough food.
That
But
sounds really interesting.
maybe they'll give extra credit for if you beat me in some of these games. Remember, I grew up with these. I don't know how far back he's going. I don't know if we're doing Atari. Yeah, retro. Yeah, it's got to go pretty. Hey, how many of you have heard of the magazine Nintendo Power?
I've surrounded myself with retro games my entire life.
So Nintendo Power, I'm in that magazine. I'm trying to remember which month it is. It was when the second Mega Man game came out. When the cover of it was Mega Man all in silver. I'm in there for a kind of a hack for a game called Super Black Bass on Super Nintendo, I think, for catching the biggest fish. And
I'm
how
sorry, that doesn't seem to line up with one.
Yeah, it's not impressive, but I am in there. I couldn't have been that old. I
I
must
was
have
Mega Man 2 on the cover of an
12
SNES
maybe.
of the SNES era.
Back then you used to have to send in a Polaroid, a picture, a mailing address with a stamp. We didn't have email. I mean, the internet did not exist. We had dial tones. We had our calluses from building, for dialing a number. You would ride your bike over to your friend's house to ask if they can come out and play. There's no texting at the time.
Are you sure there wasn't like Mega Man X on the cover?
The issue is all silver. So the whole issue, the magazine cover is in complete silver and it's Mega Man on the front. I don't remember which version of Mega Man. It might have been Mega Man X, but that was the one. So I'm in there for Super Black Bass. All right. So come and check out that thing next Wednesday starting at 3 p.m. and we'll play some games or whatever. Okay. So as I was saying, we're kind of looking forward a little bit, but we're seeing how these languages are built. And they're built in terms of inheritance, where a print stream is a file output stream, which is a object stream, which is an object. And every single class in all object-oriented languages at some level come from generic object. That's what makes an object-oriented language work. So when they built C++ or built Java or C# or Objective-C or Swift, what they had to do is they had to bring into existence the minimum viable product for what an object is. The most generic object you can think of. So if I click on this, this is what an object is by default. And you see the very top thing here, we have a function called clone. And clone returns a copy of this object. So if you had a function that took in a object as a parameter, like a fraction, and you wanted to work with that as if it was a copy. So any changes you make are not felt outside. What you would do is you would clone it either before you passed it in or after you receive it, so that you know you're working with a copy, not the original memory. So it lets you pull it off without a special pointer syntax thing, but that function, that feature had to be built into the generic object type in order for you to pull off the idea of passing in a object effectively by value. It's still being passed in by address, so it's you're being efficient with memory, but the memory you change is not the original memory, so you're not breaking your original version, in this case, of our fraction. I would say in general, if you just think about typical programming practice, this isn't a significant issue. Like, I can probably count on one hand the number of times I've ever had to actually call the clone function. It's not necessarily that common that you would take an object as a parameter, want to make changes to it, but explicitly not want those changes to be felt outside of this function. Usually, if you're changing something, you want those to be permanent changes. So almost the clone is not a commonly called thing, but there is a way of accomplishing that if you so desired. All right. Let's get back here to the code. All right. So let me get our stuff back in here. All right, so here's our fraction. We have two fields, a numerator and denominator. We have a constructor that takes in the numerator, takes in the denominator, and sets this fraction's numerator equal to whatever numerator was passed in. It sets this fraction's denominator equal to whatever denominator was passed in. Then we have a single function here called display that will display the numerator and denominator of this particular fraction. So now I can create a couple of instances of fractions. We saw that when I printed out F1 and F2, we got memory addresses. So they live somewhere in memory. So we are passing them by address. They are effectively pointers without having a special syntax to be a pointer. And then we are asking F1 to call upon one of his abilities, display. And what does display do? Display says, print some stuff out to the screen, print this fraction's numerator, followed by a slash, followed by this fraction's denominator. And remember, on our notes here, I mentioned that the this keyword is how an object refers to itself from within itself. And let me drive that point home here. When I have F1 calling his display function, why can't I say F1.numerator there? Because that's really the fraction whose numerator I want to deal with, right? A couple different reasons why we wouldn't want to do that. But the most obvious reason here, in this particular case, why can't I say F1.numerator here?
No, I didn't put display.
We don't have an F1. So F1 is not a local variable here. It's not a local variable here. It's not a variable here. A variable name F1 is not accessible in this scope. So it's going to yell at me. It says, I've never heard of F1. Why? Well, F1 exists out here inside of driver, which is inside of the class called driver. Well, it's in main rather, inside the class called driver. The class called fraction is a completely separate class. They're in different zip codes. All right. So variables that were defined inside of here are not accessible inside of here. Now we can make a point here though. I can say system.out.println F1. And then I'll print out F2. And then what I'm going to do is inside of display, I'll print out the value of this. Remember, this is how an object refers to itself from within itself. So when F1 calls his display function, the very first thing it'll do is it'll print out this. That is the memory address of F1, which should identically match F1 out here. So we're going to get the memory address for F1, followed by the memory address for F2, followed by, inside of this guy, the first call will be the memory address of F1. Why? Because the original call to display here came from F1. F1 was calling his version of display. And here, I'll just go ahead and I'll remove F2 from this example, just so we can see it. So now I'm only dealing with one fraction. I bring a fraction into existence. I display its pointer. Then I ask that fraction to display itself. And the first thing it does in there before displaying the actual fraction is he displays the value of this. This right here will be the identical value as F1 is there. This is how an object refers to itself from within itself, because it does not have access to that variable F1. Remember that thing I said don't do? Put that back. All right. Those guys are the same value, right? Which means that inside of an object, this is a synonym for whatever variable you had when you called upon this thing. Because we don't have access to F1 in here. We don't have access to the this keyword out here. Or at least we don't have access to F1's, this version of this. Technically, if I was inside here and I tried to output this, what would it be? This is actually an error, but what I'll explain why, but it muddies the water a little bit, so don't try to get too deep into this. But what would this, when I say system.out.println this here on line 28, what would it be attempting to display? Remember that this keyword is how an object refers to itself from within itself. In this case, we are inside of what kind of object? What object are we within here? Yeah, main is a function that lives inside of a class called driver. So what we probably meant here, by the way we written, I mentioned that it's actually an error for a reason that we can't really talk about in detail. I'll mention it, but we can't get too deep into it yet because we don't know what static means quite yet. But we probably, when we say this here, we're probably referring to the instance of driver that we're in. When this here is the instance of fraction that we're in. So this is how an object refers to itself from within itself. In this case, we are inside of the fraction class. So this is how that fraction talks about themselves. And as the code we've been having, I think I have some stuff commented out right now. We have two fractions that have been in play. We've defined F1 and F2. So there are two instances of fractions out there. Just like there's a whole bunch of instances of humans in this room, right? Each one of us are human beings, but we have some specific attributes that differentiate ourselves from each other, right? But we're still human. All right. So what I'm effectively doing here is I'm trying to print out the address of driver. Now this isn't going to work. It's going to tell me that this keyword doesn't exist here, and I'll explain why. Non-static variable this cannot be referenced from a static context. I mentioned that static keyword. So main is something that is labeled as static. Static means that it's owned by the class itself, not instances of the class. The this keyword only functions when we're dealing with an instance. So for instance, if I, again, another word, you can't teach it without saying, you can't teach about instances without saying instance. You can't teach about this without saying this. If I had a piece of paper up here that was a blueprint for building a human being, all right, and we had access to some of the code in there, this means nothing inside of that because that is the class itself. A human does not exist. It's just the plans for making a human. All right. So when we are in a context like main here, that has been labeled as static, we're saying this is not something that is directly associated with any particular copy of driver. This is driver itself on a global scale, has main, therefore there is no such thing as it referring to itself because it only exists once. It doesn't have to differentiate itself from other things. That will become more and more clear to you as we get into static. We're not touching that yet. I just wanted to kind of give you some examples of the pitfalls you might bump into. So typically in main, you will not be using the keyword this. You won't see it. But when you have instances of variables, like in this case, we have an instance F1 that's of type fraction. So F1 is a fraction. And now F2 is a fraction. When F1 calls his version of display, and we reference this inside there, F1 is talking about himself. When F2 calls his version of display, and we say this right here, that will be F2 talking about himself. So we write it generically inside of display where whoever called display, that person has a local variable called this that is provided for us. And that variable is how that guy refers to themselves. All right. So as I have it written right now, here, I'll print both of these out. We'll see F1 and F2 will be the same addresses as display for F1 and F2 displays. So here's D0, DC. Here's this inside of F1's display. That's the D0. And here's this inside of F2's display. There's the DC. All right. Okay. Now, I'm going to go ahead and take my class fraction stuff. I'm going to cut it. I'm going to use that identical code, but I'm going to put it in its own file. So I'm going to go up here. I'm going to create a new file. Now, my class is called fraction, so it must be inside of a file named fraction.java with a capital F. Say this again, you were breaking up.
I got a question. Line 11, how does that interact with the display function?
Let me go back here. Line 11.
Yeah,
This guy
how
here.
does that?
It doesn't. It does not call display function. F1 right here, we're printing it out. So that's why it's displaying to the screen. We're saying system.out.println, but all we're doing is we're printing out the value of the variable F1. F1 was defined right here. Its value is a memory address. It's a memory address that then points to the actual fraction somewhere in memory. So she was asking here on line 11, how does this interact with the display function? And the answer is it does not. This is 100% living inside of main, just talking about variables inside of main. This is no different than saying int a is equal to 5, and then me saying system.out.println a. And this will print out a 5. So the value of a is 5, the value of F2 is some memory address, the value of F1 is some memory address. We just happen to see the correlation between the memory address of F1 here and F2 here to what F1's display function thinks his version of this is equal to, and what F2's display function thinks his version of this keyword is equal to. So inside of the class fraction.
And what's the point of writing void display?
Well, why is it written void display here? Because display doesn't return anything. Say that one more time.
What's the point of even writing it at all?
Well, because we want fraction. We would never do this. This is probably something we're not interested in. I only wrote it so that we can see that comparison between F1 and F2 when they're in scope, and then how this keyword inside of the display function is the same memory address, even though there are different variable names to access that. Outside of it, we have F1 and F2 that hold those memory addresses. Inside of our fraction, we have this. This keyword is the memory address where that particular fraction lives. So I would end up removing that code there. You would, I mean, it's not really helpful to know what the memory address of something is in really any language, but Java's kind of doubled down on that by saying we're not even going to give you syntaxes for working with memory addresses. But this was proof of concept that F1 and F2 in main are equivalent in value to this inside a fraction, depending on whose version of display was called. If it was F1's version, this is a synonym for F1, same memory address. If it was F2's version of display, this is a synonym for F2, same memory address. All right, so I would probably get rid of that line there too, because really we wrote display with the purpose of a fraction having the ability to display itself to the screen. And when we think about a fraction, we don't really care about its memory address. We care about its numerator and denominator. That's what a fraction means to a human being, right? We think about a fraction, we think of something with a numerator and a denominator. All right, so I've moved it into its own file here, just fraction.java. It has to be called fraction.java with a capital F because that's the name of my class. Notice this guy does not have main in it. All programs begin and end with main. So until we get a little deeper and can explain this in more detail, you will only ever have one class, even if that has main in it. Even if we have 500 different objects we're going to define in here, only one of those classes will have main, because that's where our program begins and ends. Now, those classes might create references to each other, okay, but there's only going to be one main. So fraction keeps track of a numerator and denominator. It has a constructor for building a fraction, and then a fraction has the ability to display itself. So out here in driver, I would create my two fractions, F1 and F2, and then I would ask each one to call his display function. The first one's going to show me 1/2. The second one's going to show me 3/4.
Okay,
And notice now I've kind of encapsulated, it's probably an encapsulation example, but I've moved my details about fractions into its own file. As long as it's in the same directory, in Java, that's called the same package. It gets a little bit. Packages in Java are kind of like namespaces in C++, which we never really got into in terms of writing them ourselves. We're going to say that that's kind of another level of organization that isn't all that important for learning programming, but that's what it is. A namespace or a package is just a way of organizing your code in such a way to know where you have to go for different values, things like that. But for right now, when we're dealing with Java, we're just going to assume everything is in what's called the default package. And the default package basically says, if your files live in the same directory, they have access to each other. That's the ultimate punchline for us. I'm not going to talk about packages as they relate to Java again for a while. At some point, it might come back up or whatever, but we're not going to be differentiating that in here because it's not a programming skill thing. It's an organizational tool. All right, so because fraction lives in the same directory as driver, we just put it in its own file to keep our file with main in it nice and clean. This is our whole program right here, right? Just has some supporting staff that's behind the curtains that we can come in here and make some changes to it. But ultimately, when we look at our program, this is our quarterback. All programs begin and end with main. Main saying define two fractions, tell each one to display themselves. All right, now, remember, we wanted to have fractions able to add themselves to each other. So what I'm going to do here is I'm going to write the header for a method that is going to be your homework. So I want to have a function called add that takes a fraction as a parameter. So this guy is going to add this fraction. This is the object whose add function was called. So this dot numerator, this dot denominator, that is this particular fraction's numerator denominator. And we want to add that to F's numerator and denominator. And ultimately return a fraction. Like this. And the way this would be used, so I'll show you in main the way I want you to test this, is we would say fraction answer is equal to F1 dot add F2. Let's call this answer 1. If I say fraction answer 2 is equal to F2 dot add F1, and then I say answer 1 dot display, answer 2, dot display. These guys will both have the same answer. The difference is in this case, I asked F1 to add himself to F2. Where in this one, I said F2, add yourself to F1. But both of them are going to produce the same output. Because it doesn't matter which fraction we're adding to what other fraction. We're getting fractions that adding a fraction to another fraction gives you the answer. And I'm working with the same fractions here. It's just we're just changing whose version of add we're calling. So you're going to get the same answer here as proof of concept. But in the first example here, we're having F1 call his version of add. And when F1 calls his version of add, this is F1's stuff. And F in that example would be F2's stuff. In the second one, when we call F2's version of add, this is F2. F here is F1 that was passed in. All right. So you want to make this code function where these two lines should give you the same output, which is the sum of these two fractions. And the way you're going to call that function is just like that. All right, so I'll give you this as a starting point. Fraction Java, we'll call that good enough. And so that's due on Tuesday. So start effectively writing a function you've previously written. You're just writing it now in terms of objects. All right, so you can go back and look at your old functions for the logic of finding the common denominator and doing the cross multiply stuff. Ultimately, you're going to return a brand new fraction object instead of a fraction struct, which was the last version of this assignment. All right. Questions, comments, concerns, bribes.
So this will be on Slack.
All right, I'll see everybody on Tuesday.
So this will be on Slack then.
I think I hear you trying to talk, but you're breaking up. So if you want, write it in chat.